In this video, we're going to walk through the steps of the PERT method. The PERT method using tables 13.4, 13.5, and 13.6 in the text. If you don't have your worksheet laid out like this, you'll need to pause the video and lay it out. Don't worry about putting these equations in here. I just put them in as teaching tools. I indicate the place or the variable for each of these values where they appear in the equation. Be very careful to get these times in correctly. They're provided in the text. So go ahead and take a moment and complete this workbook. Now in the text we look at the Portovac problem, and one of the things that they want to do ultimately is determine the probability of meeting the project's 20-week deadline. That's one of the characteristics of the PERT method, is that it becomes a probabilistic model for the project. So you can calculate probable completion times, and that can be important. All right, let's walk through the model. We're going to do this the same way once we get to our forward and backward pass. We're going to do this the same way as we do the CPM, the critical path method. But our difficulty is we need to go ahead and calculate our time, variance, and standard deviation. Now the expected time is calculated by an optimistic time, a most likely time, and a pessimistic time, which is more realistic. Rarely do we have an exact time. We normally have a range of times. This represents the range of times. And the way we calculate the expected time is just to weight the most likely time 4 times heavier than the other times, and then take an average. So we're going to have 6 values. We're going to have 1 A value, 4 M values, and 1 B value. Then with 6 values, we're going to find the average. So we're going to divide by the number of values, or 6. That's what this equation says. So let's set this up. Equals our A value plus 4 times our M value, our most likely time, plus our B value. We'll take that and we'll place it over 6, and we get our expected time. I'll go ahead and center these values so they're a little bit easier for you to read. And once I have that done, I'll just copy it down. There we go. There are our expected times. These are the times we will use. Now, for the probabilistic portion of this model, we're going to calculate a variance and a standard deviation. Here's the formula for the variance. The 6 here doesn't indicate the same thing that the 6 here indicates. The 6 indicates the number of standard deviations for our model, how accurate we want the model to be. So this would change depending on if you wanted a 95% probability, 99% probability. But for now, we're just going to use this 6 value. So what we'll do is we'll find our range, which means we take our biggest value and we subtract it from our smallest value. That gives us the range of values. We divide by 6 in this case, and of course it's a variance, so we're going to square it. We want to take out the effect of negative values. Go ahead then and decrease that down a little bit, and I'll copy these down. There we go. And the standard deviation, as we've said many times in the course, is simply the square root of the variance, and that's an important element here. So there's our square root of our variance, gives us our standard deviation. Get rid of a few decimals, and there we go. Now we can go ahead and determine our earliest start times and our latest start times and complete the model portion. Remember, the earliest start time for an activity with no predecessor is 0. And the earliest finish time for all activities on the forward pass is the earliest start time plus the expected time to complete the activity. And that's where we have to be careful to use this value. That's the value we've calculated here. Now that's going to be true all the way down, so I'm just going to copy it down. It'll be incorrect, though, until I get these values completed. Again, B has no predecessor, so it starts in period 0. C is preceded by activity A, so C starts when A finishes. The same with D, preceded by activity A. D starts when A finishes. And also E starts when A finishes. F is preceded by activity C. It starts when C finishes. G is preceded by activity D. G starts when D finishes. H is preceded by activities B and E, both of which have to be finished. So I take the largest value, the max of B and E. B and E. There we go. Get quite a distance here, so you have to watch, be careful. I is preceded by activity H, so I'll just go up here and get the finish time for H. And then J is preceded by F, G, and I, so it's the max of activity F, G, and activity I. And that gives us a 17-week finish time. We need to determine how many end nodes there are. So we're going to look through our predecessor list to see who does not appear. Those are end nodes. We have A, B, C, D, E, F, G, H, and I. Only J is missing, so J is the only end node in the model. Go ahead then and bring J over to start the backward pass. If we know that activity J finishes in the 17th week and that it takes 2 weeks to complete, we can deduce that it started in the 15th week. We are on activity I. We look to see activity I precedes only activity J, so J could not have started until I finished. And if J did start here in week 15, that means that I finished in week 15. So again, I deduce that I finished in week 15, and I know that if I have the finish time and subtract the duration, expected time of the activity, I can get the start time. That's going to be the case all the way back, so I'm just going to copy that up so I don't have to do it every time. I'm on activity H. I look for H here. Precedes only activity I, so I'll get I's time here. I'm on activity G. Precedes only activity J, so I'll get J's time here. I'm on activity F. F precedes only J as well, so I get J's time. I'm on activity E. E precedes activity H, so I'll go down here and get H's start time. I'm on activity D. D precedes only activity G, so I'll go down here and get G's time. I'm on activity C. C precedes only activity F, so I'll go down here and get F's time. I'm on activity B. B precedes only activity H, so I'll come down and get H's time. And activity A precedes several, so I need the minimum, the smallest value, because none of the activities that activity A precedes, so none of the activities that follow activity A could have started until A finished. So whenever the first activity that follows activity A starts, A must have finished. So we get the minimum here. So a minimum of C, D, and E. And that gives us our latest finish time for activity A. Now we can calculate the slack And I just use finish times. You could use start times, take the latest and minus the earliest. And there's our slack. I'll just copy this down. Now this time, I'm going to put a 1 here in the critical path instead of the letter. You really do need to put a 1 in this case. I'm going to say equals if the value to my left equals 0, then 1. Otherwise, I'll just leave it blank. 2 double quotes next to each other. And I'll copy this down because I'm going to need to use this 1 in a calculation. So now when I answer these questions, I put in my critical path. I have to kind of take a look at the 1 and draw a line back across. It's not too hard. So my critical path is A, E, H, I, and J. All right. Just have to write those in. That's how you do it. Project length. The project length is always going to be the first step of the backward pass, the latest finish time for the final activity backward pass. Project variance, this is why you need to put a 1 over here. The project variance is the sum of the variances on the critical path. Now you could do that manually, add this variance to this variance to these 3 variances. But if you're doing some forecasting, some modeling with this, those things may change. So it's best if you use the sum if function. The sum if function asks for the criteria range first. There's the criteria range. It asks what value we're looking for, in this case a 1. That's where you put a 1 there. It makes it nice and easy. And then it asks for the range to sum. Well, if there's a 1 there, we want you to go over and get the variance and add that up. And this is going to give us then the variance for our critical path. Then the standard deviation. The only way to calculate the standard deviation here is to take the square root of the variance. You remember that relationship. The standard deviation is always the square root of the variance. So now we have a standard deviation. We can take that out. Now with the standard deviation, we can calculate the probability of finishing this project in a given period. Now in the text, they have you calculate a z-score and use the standard normal distribution. I don't understand their fixation with the z-score. Unless you're stuck with a table, there's no reason to use the standard normal distribution. We have access to any normal distribution that we need. So we can go ahead and use the normal distribution and get this answer here. It's a lot quicker, saves a step, it's more intuitive. So we're going to use the norm.dist function. The norm.dist asks us for x value. Well, in this case, they want to know less than or equal to 20 weeks. Well, that's perfect in this continuous distribution. So the x we're looking for is 20. We have a mean. We've calculated our mean right here. It's the project length. We have a standard deviation. We just calculated it. That's what it wants. And then it's a cumulative distribution. So the answer to this question is always true. Press enter. Go up here and take out a few decimals. And we see that we have about a 97, or let's put one back in there, a 96.5% chance of finishing this project in less than 20 weeks, which is good. And of course, if we wanted to know greater than or equal to 20 weeks, we just take 1 minus this value and we get the probability of finishing in greater than or equal to 20 weeks. This is how you find the critical path and the project standard deviation using the PERT method in Excel.